Every recovery operation operates against a hard boundary defined by time and terrain. For the Lockheed P-38 H1LO Lightning bearing United States Army Air Forces, serial number 4266534, that boundary spanned roughly 60 years. The objective in the years 2003 through 2004 was straightforward on paper. Extract the intact aluminum airframe components from the dense jungle plains for private museum restoration. The operational reality involved locating and securing a multi-ton twin-engine fighter aircraft that rested roughly 10 miles south of But Airfield in New Guinea. The stakes of this operation were entirely procedural. This was not merely the retrieval of derelict hardware. The reports suggest the pilot may have survived the landing and left the immediate crash area, but his fate was never confirmed and no remains were recovered. In U.S. Army Air Force's records, he was later presumed dead, yet the loss remained unresolved on the ground. That singular fact changes the legal and forensic baseline of the entire recovery effort. The aircraft belonged to the 431st Fighter Squadron of the 475th Fighter Group. It was flown by Second Lieutenant John R. Weldon Jr. When a pilot is unaccounted for, the wreckage ceases to be just an engineering artifact. It becomes a sensitive loss site, where any work carries an obligation to document what is disturbed and to defer to the appropriate authorities if evidence of the missing airman appears. The salvage team led by Bob Jarrett in 2003 faced the challenge of executing a heavy mechanical extraction without compromising a site where human remains or critical survival gear might theoretically exist. The 60-year gap between the loss of the aircraft and the arrival of the recovery team introduced massive evidence degradation. Organic materials, flight logs, and soft equipment break down rapidly in a tropical environment. What remained for the salvage crew was the heavy aluminum primary structure. The physical footprint of the P-38 appears to have been preserved largely because of the forced landing geometry. A wheels-up belly landing distributed impact loads across the lower fuselage and wing structure, reducing the chance of immediate fragmentation. Later documentation suggests the aircraft remained largely in one piece as it came to rest. It slid into the high concealment terrain of the Sepik Plains. This dense vegetation effectively swallowed the visual profile of the twin boom fighter. For decades, the environment acted as a natural screen, isolating the wreckage from airborne observation and ground-level interference. The isolation allowed the primary structural joints, the outer wings, and the tail booms to survive in a highly recognizable state. Evaluating the recovery objective requires understanding the specific hardware target. The P-38 Lightning is not a conventional single-fuselage aircraft. Its design incorporates a central cockpit nacelle flanked by two massive engine booms that extend aft to support the tailplane. Extracting such a sprawling footprint from a remote jungle location demands rigorous logistical planning. The salvage operation had to secure the site, catalog the visible structural segments, and prepare the airframe for a transition out of the isolated planes. The team recognized that the external aluminum skin was intact, but they had to verify the integrity of the internal load-bearing members before any lifting forces could be applied. Decades of moisture, heat, and localized corrosion could have weakened the factory splice points that held the aircraft together. Before the physical extraction could begin, the baseline condition of the wreckage had to be documented. The priority was identifying which sections of the aircraft possessed enough structural continuity to survive a heavy lift operation. The presence of a missing in-action pilot meant that the center nacelle required specific handling considerations. The recovery crew was forced to navigate the friction between preserving a potential forensic footprint and executing an industrial salvage operation. Every touch on the airframe had to be weighed against the risk of destroying historical context. Those surviving outer structures became the only realistic museum-grade prize. The sheer size of the components dictated the pace and method of the site breakdown. The 2003 operation set the chain in motion, secure the perimeter, map what was visible, and stage the big pieces for movement. Once the crew confirmed the structure could tolerate handling loads, the mission shifted from observation to extraction planning. The next step required understanding exactly how the airframe arrived in this specific configuration. What mechanical state allowed the heavy twin-engine fighter to survive a high-speed forced landing without breaking apart? The trade-off edge in military aviation often forces a pilot to choose between two highly destructive outcomes. On January 18, 1944, a single combat damage event forced exactly this kind of calculation, creating a severe trade-off between structural survival and catastrophic in-flight breakup. The aircraft was conducting an offensive fighter sweep over WWII, New Guinea. During this mission, the flight was engaged by Japanese fighters. The resulting attack inflicted critical damage to one of the two Allison V-1710 engines. In the confusion of combat, and the exact failure chain is hard to reconstruct, but the hit immediately altered the flight parameters of the heavy fighter, placing the pilot in an emergency with seconds to react. When one power plant on a twin-engine aircraft catches fire, it creates an immediate asymmetric thrust and drag penalty. The disabled engine acts as a massive air brake, while the functioning engine on the opposite side induces a severe yawing moment that the pilot must constantly counteract with heavy flight control inputs. More critically, an uncontained engine fire in the inboard nacelle threatens the primary structural integrity of the main wing spar. The pilot must execute a forced landing before the intense heat causes a structural burn-through. A spar failure in flight would snap the wing entirely, rendering the aircraft completely uncontrollable. But faced with this rapidly closing time window, Second Lieutenant John R. Weldon Jr. had to put the burning aircraft on the ground immediately. He selected a flat expanse of dense vegetation for the emergency landing. Deploying the landing gear in unimproved, heavy brush creates a lethal hazard, as the nose wheel would dig deep into the soft earth and violently flip the massive aircraft onto its back. To prevent this inversion, the pilot executed a wheels-up belly landing. With the landing gear retracted, the main gear tucked into the booms and the nose gear stowed in the center nacelle, the flat lower surfaces of the fuselage and engine nacelles distributed the forward momentum horizontally. The aircraft slid across the dense vegetation, bleeding off speed until it came to a complete and upright stop. The pilot survived the initial impact and the subsequent violent slide. However, the completion of the physical landing introduced a new, critical operational constraint. Resting upright in hostile territory meant that radios and identification friend or foe equipment could be at risk of enemy capture. Many airmen were trained to deny sensitive equipment if capture was likely, but what happened at this site is not fully documented in the open record. At some point after the landing, a fire consumed the cockpit and forward center section. The cause is uncertain. It may have involved deliberate denial of sensitive equipment, a grass fire, combat damage, or a combination. But the burn pattern appears concentrated on the center nacelle. The outer aluminum wings, the twin tail booms, and the horizontal stabilizer appear to have remained largely intact compared with the burned center pod. The heavily burned central cockpit nacelle is the site's strongest physical clue. It confirms that significant fire took hold in the cockpit and forward center section during or after the landing sequence. That burn scar reshaped everything that followed. The center pod collapsed into fused metal, while the outer wings, twin tail booms, and horizontal stabilizer stayed recognizable by comparison. With the main connection between left and right effectively destroyed, the wreckage aged as separated, heavy structures instead of a single rigid airframe. And that raises the next problem. How does a heavy aluminum airframe sit for decades in wet tropical ground without simply sinking out of reach? Visual sensors are fundamentally defeated by organic cover. When an aircraft comes to rest in an environment dominated by high concealment terrain, the initial search parameter is entirely vertical. The optical footprint of a twin-engine fighter is massive, but it disappears instantly if the surrounding flora is taller than the highest structural point of the airframe. In the Sepik plains, this biological screen consists of kunai grass. In season, it can grow in dense, rigid stands that rise above a person's head and erase the outline of anything lower to the ground. Because the P-38 came in on its belly, the highest points of the remaining wreckage sat below that living wall, and aerial passes could see nothing but an unbroken sea of green. However, concealment is not the same as preservation. A heavy metal object in saturated tropical soil often sinks and corrodes quickly, but dense rhizomes and roots can form a tough, near-surface mat that sometimes helps distribute weight and slows submergence. That does not stop corrosion, but it can help keep large sections from disappearing immediately into deep mud, leaving a wreck in a state of slow, uneven decay rather than instant burial. This balance of concealment and partial support may have helped hold the airframe near the surface until the year 1997. Localization in this type of environment often depends on brief moments when the cover thins and the outline becomes readable from above. In 1997, the wreckage was photographed from the air, providing the first clear documentation since the loss. And those images showed the twin boom outline still recognizable, with major outer structures, including wings and tail components, apparently still present at the surface. This photographic proof transformed the site from an unconfirmed anomaly into a highly viable target for physical salvage. The visual confirmation meant that a recovery operation would not be a blind excavation into deep mud, but rather a surface-level disassembly. By the year 2003, Private Salver Bob Jarrett and his team utilized this baseline intelligence to mount an expedition into the plains. Inside the kunai plane, the problem was not just concealment, it was movement. Every meter had to be cut, dragged, and staged by hand, in ground that fought every tool. A surface expedition cannot simply drive heavy ground equipment to the coordinates. The dense grass, tough root mat, and saturated ground can make vehicles impractical, sharply limiting what can be brought in overland. In practice, the team's options were constrained to light equipment on the ground and support from the air where possible. When the salvage crew breached the final perimeter of the grass and stood beside the airframe, the 1997 photographic intelligence was physically verified. The aluminum skin was heavily oxidized, but the primary load-bearing structures remained solid. The environmental isolation had prevented human interference and looting, leaving the factory splice points and structural joints undisturbed. This integrity was essential because the complete lack of ground access paths meant that towing the intact airframe out of the plains was geometrically and mechanically impossible. The physical footprint of the aircraft had to be reduced. The recovery team possessed the target and verified its structural integrity, but they were trapped in an environment that forbade the use of heavy cranes or transport trucks. Once localized, how do salvers extract a multi-ton, rigid airframe from an inaccessible plane without heavy ground equipment? With no practical ground access, the only viable lift was by rotorcraft, and no civilian helicopter could carry a complete P-38 in one piece. In the year 2003, the salvage team ran into a procedural constraint even before the first cable went on. It was not just a question of lift capacity or corrosion. It was the status of the loss itself. The pilot of this specific aircraft was still classified as missing in action. With no remains visible during the baseline assessment, the crew logged what they disturbed and treated the burned center section as a sensitive footprint as the work moved forward. With the site cleared for structural interaction, the engineering challenge of the 2003 recovery dominated the operation. Ground access was limited, so the team planned to remove only the most intact outer structures and to move them out by helicopter as separate sling loads. That meant separating the wings and tail components from the burned center pod, stabilizing each piece, and lifting them out one at a time to a staging area beyond the grass. Then the helicopter began the slow arithmetic of recovery. One sling load at a time, flown out to a staging area beyond the grass. The major outer structures were extracted and positioned for onward transport, while much of the burned center section appears to have been left behind. Mechanically, the lift worked, and that is exactly where the next question cuts in. Did a private team have the legal authority to remove sovereign war materials? But across an international border, aluminum still answers to paperwork. In 2003, the private salvage team possessed the physical wreckage of the P-38, acting under the belief that their locally acquired permits authorized the removal. That assumption would be challenged publicly a few years later. In 2006, Papua New Guinea's Public Accounts Committee reopened scrutiny of aircraft recoveries and export permits. And building on earlier moratorium policy and rising concern over war surplus leaving the country. The inquiry traced how approvals were issued, summoned officials to account for the paperwork, and followed the administrative path from remote crash sites to commercial shipping. When investigators drilled into the P-38 permits tied to the 2003 operation, they concluded that provincial and local authorizations had bypassed the required National Museum oversight. The committee ruled the permits invalid, exposing a structural failure in enforcement. A recovery could be engineered in the field, yet still stand on broken authority. The resulting government report documented a widespread failure of customs enforcement and statutory protection, fundamentally altering how future recovery operations would be permitted. The immediate consequence of the 2006 inquiry was a complete shutdown of foreign salvage operations within the country for several years. The state reasserted its absolute ownership over all remaining crash sites, enforcing a strict boundary against further mechanical extractions. However, the legal enforcement arrived too late to stop the physical export of this specific aircraft. The multi-ton outer wings and the distinctive tail booms had already cleared the commercial port and crossed international waters. The Public Accounts Committee inquiry successfully documented the administrative failure, but it could not physically recall the exported aluminum. That mismatch cast a permanent legal shadow over the recovered hardware. The metal was safe offshore, but the chain of custody was officially condemned by the sovereign owner. With the wreckage legally scrutinized and removed from the jungle, what is the final disposition of the extracted hardware? When incomplete aircraft structures arrive at a museum facility, restoration teams face a binary decision. They must either display the fragmented hardware as a static diorama or absorb the surviving metal into a composite airframe. For the recovered outer wings and tail booms of the Lockheed P-38, the choice was integration. This process requires a strict separation of an aircraft into two distinct assets. The first asset is the physical aluminum structure. The second asset is the administrative identity, dictated by the manufacturer data plate and the original military serial number. In the high-end restoration market, these two assets can follow completely independent trajectories. A partial wreck rarely contains enough structural integrity to fly again on its own. Instead, it becomes a donor airframe. The viable physical components are stripped, treated for corrosion, and legally transferred to supplement another incomplete fuselage. Meanwhile, the historical paperwork is sold separately as a viable restoration project to an independent buyer. The physical remnants of the twin-engine fighter followed this exact division. After clearing customs, the multi-ton aluminum assemblies were transported to South Australia. At this facility, a private museum was already engaged in the complex restoration of a different Lightning, designated as 42-66841. The newly imported Sepik planes assemblies were reportedly used as donor material to replace missing wing and tail structure on that project. In the process, the recovered pieces ceased to exist as a separate, displayable aircraft and became part of a composite restoration tied to a different serial identity. While the heavy metal was cannibalized in the southern hemisphere, the administrative identity of the aircraft traveled across the Pacific to the United States. The data plate and the legal provenance of 42-66-534 were acquired by an American entity. This allowed the identity of the aircraft to be legally resurrected strictly on paper. Records later show a civilian registration tied to the identity of 42-66534 under the N number N66534. The paperwork establishes an administrative trail, but it does not by itself describe how much original material survived or what any future rebuild would physically consist of. Any aircraft ultimately flying under that registration would stand or fall on the documentation and inspections required by the FAA. The legacy of the physical machine is entirely fractured, divided between a static museum display in Australia and a dormant registry file in North America. This fragmented mechanical outcome stands in stark contrast to the human baseline of the incident. The mechanical systems of the fighter were mapped, recovered, and repurposed, but the operator of those systems was not. Second Lieutenant John R. Weldon Jr. got the aircraft onto the ground and denied what he could. After that, the trail belongs to silence. Following the end of hostilities, the military apparatus initiated a mandatory administrative transition for unrecovered personnel. On January 16, 1946, the official status of the pilot was legally transitioned to a declaration of death. The 2003 recovery operation successfully extracted the targeted industrial hardware from the jungle environment, but it did not yield any new forensic data regarding his final location. South of But Airfield, the Lightning's full footprint is gone. What remains in the high grass is the fused residue of the central nacelle, an immovable marker for an unresolved missing in action site. The operational objective to recover the aircraft succeeded mechanically, Yet it triggered a severe legal boundary that shut down an entire region to future salvage. The surviving components now exist exclusively as donor parts and a paper registration, leaving the original crash site as a permanent, incomplete forensic marker.